Okay, so yesterday when we left our chemistry heroes, we had talked about, and today is the 5th of May, we had talked about equilibrium vapor pressure, and we said that in a closed system, so we have like a little closed flask or vessel of some sort, that the pressure exerts some amount, the vapor exerts some amount of pressure back on the liquid. And what you have in your hands is a vapor pressure chart. Have you seen a vapor pressure chart outside of this class? I know a few people in the other class had, and you know where they saw it? On the ACT. So these do show up. These and triple phase diagrams show up on the ACT. So getting a chance to use them in here is a nice little ACT score booster. The pressure that a vapor exerts on its liquid phase changes with what? Looking at that chart might give you a clue. Temperature. Yeah. It changes with temperature. And the higher the temperature, the more pressure the vapor exerts on the liquid phase. So we'll call this side VP and we'll put it in torr. And this side is temp in degrees Celsius. Okay. Well, just so happens that there's this funny relationship between vapor pressure and temperature. If we have that little closed system that we were talking about back here, at the point where the pressure that the vapor is exerting is equal to atmospheric pressure, guess what happens? Pressure the vapor is exerting is equal to atmospheric pressure. This stuff boils. So if you remember back to our conversation about boiling versus evaporation, what's the big difference between boiling and evaporation? Where do the molecules make the break from in evaporation? Yes. Boiling's inside the water column. So at the point when the vapor is exerting as much pressure on the liquid as the atmospheric pressure that was holding those molecules down together as a liquid, they all escape into the vapor phase. They all go to vapor and the stuff boils off. So we can take a vapor pressure chart. Let me cut these guys out. Oops, gesundheit. We can take a vapor pressure chart and we can look at the point where vapor pressure meets atmospheric pressure. So if this is in torr, so let's say this is 760 torr. Let's say for substance, whatever, 175 Celsius. Oops. So, under normal atmospheric pressure, at what point will this substance boil? We just drop a line straight down, at 175 Celsius. So wherever the vapor pressure line, at whatever temperature the vapor pressure line meets atmospheric pressure, that's the normal boiling point of a liquid. Okay, that's the point at which all the particles just escape into the vapor phase. We can ask a bunch of other questions, like we can look at what happens when we lower pressure or increase pressure. What I'm going to do right now, I want to see how you do with this, then we're going to go over it and walk through some more examples together. So I'm going to give you a little bit of time to work on this, and then we will go through it together. One of the things I want to talk with you about in terms of using these kind of graphs is getting better estimates based on the graph. So this graph is easy because the scales are the same. When we start into phase change diagrams, you'll see graphs that have a logarithmic scale, if you run into one of those on something like the ACT, you need to recognize what's going on so that you don't give completely, like, let's call them screwball answers. So we're going to practice a little bit with estimating spaces on a graph. So the first question, at what temperature would bromine vaporize under normal atmospheric conditions at sea level? Give me an answer, somebody. One person. Somebody who has shoelaces. Ooh, we're getting into flip-flop season. Okay. Shoelaces? Want to take it? What you got?
50 degrees Celsius.
Okay, who else has 50? Okay. Who has a different answer? No, there's no this. You have 50 or you don't. Who else has 50? You might. Does anybody have anything other than 50 and 60? Let's look at what the graph actually says. So I've tried to reproduce this to the best of my ability. And if we look at the line for bromine, it looks a lot like, and you're going to have to bear with me, up at the critical point, nope, that's not it either. It looks a bit like that. Okay? So if you look at that line, it's clearly above 50. So sorry, those of you who said 50, I would mark that wrong on a test. It's not 50. It is clearly off the 50 mark. Now there's something I'm going to tell you about your ability to estimate distance and your ability to sort of visually guesstimate. We talk about this when we talk about precision and measurement, using scales, using all those things. Humans are really good at seeing half. We are good at visually going, oh, that's half. We are lousy at going, oh, that's a third. And we're not even going to talk about your ability to go, no, that's a fourth. Nope, it's a fifth. 0.125. Forget it. You can't do it. But you can see half. So when you've got a situation like this, we know that the distance between these two represents 50 degrees. You can visually say, oh, well, there's the half mark. Well, this is, and actually on your chart, I think it's a little bit closer to the 50 than this is showing. That's half of what's left of that half. So if this is 50 and this is 100, what would the half be? 75. If it's half of the distance between 75 and 50, so you're talking about 50 plus what? Half of 25. 12.5. So that would give you 62.5. Do you have enough significant figures based on the way that this thing is marked to say 62.5? No, that's far more precise than you can be. But you can easily use one sig fig and say, yeah, about 60. And that's a reasonable estimate. So you need to make use of the spatial information that you have to make those kind of estimates. Does anybody want to redo any of their figures based on that conversation? You don't have to. Largely what I'm doing is walking you through this so that you know, yes, on the test, I would mark that wrong. Okay. For number 2, at 800 feet above sea level, atmospheric pressure is approximately 550 torr. At that elevation, what is the boiling point of water? Give me a number, somebody. Want to? Okay. Go for it. You have a green pencil. Answer.
80 degrees Celsius.
80 Celsius. Who else has 80? Okay, we have 180. Who's got something else? Okay, Claire, what do you have? 90. Who else has got 90? I have 90. Okay. Let's look at what we have here. Like I said, I've replicated this to the best of my ability, which doesn't mean it's fantastic. And the lines on this are hard to read. I will completely 100% admit that. So 550, we're looking at something in here. And the line for water passes pretty darn close to the 100. So we're almost in the same situation that we were with bromine. Let's change colors on that line. But instead of being that far off the 100, or that far off the 50, we're now about that distance off the 100. So again, it kind of looks like we're about halfway of halfway between the 75 and the 100, or between the 50 and the 100, halfway of halfway. So if we took 75 plus 12.5, what do we get? 87.5. Do we have that level of precision to say 87.5? No. But 90 is a pretty good 1 sig fig kind of answer. 80 is probably a little bit low, and I would guess that those of you who said 80 were doing a real quick visual, like, that's my guess, that there wasn't any mathematical spatial stuff going into that number, which is fine. That's why we're having this conversation. So 90 is probably your best answer for that. Have any of you ever read the back of a cake mix box? Okay, where am I going with this?
You have to keep the brownies in for, I think, a little longer.
Okay, so where I'm going is high altitude cooking instructions. You have to bake differently at elevation than you do at sea level. So we're close enough, we're 1,000 feet above sea level here. Doesn't make a difference. Once you're over about 5,000 feet, it changes how things bake. Why? Because it does what? Changes the boiling point of water. What are you doing when you bake your brownies or you bake your cake or whatever else? Couple things, but the big one is you're vaporizing the water that's in the mix. You've added water to the mix. Now there are other chemical reactions that are occurring. Your leaveners are creating chemical reactions. There are gluten reactions going on in certain types of baked goods where the gluten structure is actually hardening. But if the boiling point of water is different, yes, and I actually, when I lived on a mountain, I was at 8,000 feet and I happened to work in a bakery. So I know about high altitude baking. When we did our brownies, I believe we had to add like an extra quarter cup of flour, and then we had to turn the oven temperature down, but they had to stay in longer. So you had to accommodate that different boiling point of water. If you were baking, remember we had the example in the gases chapter of the submarine research station down at the bottom of the ocean where it's like twice the pressure. What would you have to do there? Would water boil at a higher or lower temperature? Look at the chart. It helps if you look at the chart. If you have more than atmospheric pressure, does the boiling point of water go up or down? Just point. Okay, so you can artificially raise the boiling point of water. Let's talk a little bit about this object right here. Should have cleaned it out. Anybody know what that object is? What is it? Mason jar? What else do we call it? Canning jar. Okay, we can food in these. How many of you live in a household where somebody cans food in glass jars? Okay, have you helped? You should help. Nothing on a hot September night when it's 85 degrees out and 95% humidity, like filling the house with hot steam. It's awesome. It'll curl your hair. How does a pressure canner work? Why are we talking about pressure canners? Come on, Moser. Why are we talking about this? What is a pressure canner? How many of you have ever seen a pressure canner? Okay, obviously those of you who've helped can. All right. It's a big, giant pot with a locking lid. So the lid actually has a series of little, they look almost like the parapets on a castle, on some medieval fortress. And that lid locks into place. And depending on the kind you have, it might have a little dial gauge, or it might have a weight that goes on it. Okay? And you put that canning jar full of your food with a lid on it into the pressure canner. I'll shrink that a little bit. And then the pressure canner gets filled about halfway up with water. And there's a little rack to keep the jars off the bottom and stuff, you know, blah, 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 blah. And then you seal it. And then you turn on the heat. What happens next? Should we play the stand-up, sit-down, right answer lottery, where everybody has to stand up until you give a correct answer and then you get to sit down?
Sure.
Okay, stand up. Okay. If you want to heat that food up beyond 100 Celsius, the only way to do that is to increase the boiling temperature of water. So what do? We put it in a pressure system. We lock that lid down and we heat it. And that water now does not boil at 100. And I used to have somewhere, I would love to find it again, a chart from Ohio State Extension that had, now my canner doesn't have a dial gauge. I prefer the kind I have. It has a little weight with 3 holes, and you can put it on for 5 pounds pressure, 10 pounds pressure, or 15 pounds pressure. I have no idea what that translates to in torr. I have no idea what the relationship is. But the chart I used to have said, well, at 5 pounds pressure, the boiling point of water is, and of course theirs was given in Fahrenheit, 220. At 10 pounds, it's, so I'm going to say it's 105 Celsius, it's 112 Celsius. At 15, it's 120 Celsius. I don't know what they are. I'm making these up. But there was actually a chart that said, if you want to get it to this temperature, you have to put this much pressure on it. And of course, you're holding it at that pressure for long enough that the entire, every part of the food is heated through to that very, very high temperature. High enough to kill all the bacteria in it. Now the whole vacuum thing, actually what happens is the gases that are in the jar escape under the loosened lid. Who said that? Vacuum sucks all the air out. Okay. The gases that are in there escape under the loosened lid. Because the contents are suddenly under pressure. And then as that whole thing cools down, the lid is drawn back down as the gases inside the jar shrink in volume again, and so it in essence creates a vacuum because it pulls the lid down tightly enough that the lid then seals. So that's how that part works. Okay, so that's number 3. You can also, so that's artificially raising the boiling point of water. You can lower the boiling point of water. So let's look at number 3. If a pressure canner is able to place its contents under 1,000 torr of pressure, how much is the boiling point of water elevated? Who's got a number? Who's got a number? Don't make me do shirt color lottery. Okay, somebody who is wearing blue or black. 4 of you. Who will it be? I've heard from Skylar already. I think I heard from Al. Oh, 5 of you. I didn't even see that your shirt was black. I think I heard from you.
110.
110. Okay, the boiling point is going to be about 110. It's going to be elevated about 10 degrees Celsius. To what extent would you need to lower pressure to boil water at 50 degrees Celsius? If you have to boil water, but you have a device that's only capable of heating it to 50 Celsius, how low do you have to get that pressure? Who's got a good answer for this?
Is it Molar?
Millimeters of mercury or torr? Yeah, you'd have to get the pressure down to about 100 torr. So roughly 1/7 of atmospheric pressure, which you could do in a vacuum jar. And have any of you ever seen the little handheld boilers? It's a little tiny, it's a tiny glass vacuum chamber, actually. It's a chamber that it's got liquid in it, and it's made of glass, but they've removed most of the air and then sealed it shut, and you can hold it in your hand and the water will boil. Just your body heat is enough to boil the water, because it's a very low pressure environment. So, heating it up to 35 Celsius, that's about body temp, is enough to boil it. So that's a chamber that has probably under 100 torr of pressure in it. Little vacuumy thing. Okay, under normal atmospheric conditions at sea level, what temperature is required to vaporize mercury? So remember, this is our normal atmospheric line, 760 torr. Who's got a number? Somebody wearing gray or blue. Okay, I have 2 gray who I haven't heard from yet.
I said 360 places.
Okay, who else has got 360? Yeah, that's what I have too. What other numbers do we have for that? 350? Okay, and I think on that one it's very clearly above the 350 line, so you have to be careful. I would mark 350 wrong in the test. I would definitely mark 350 wrong in the test. Okay, number 6. This is a great question. And I'm not just saying that because I wrote it. If I give you a mixture of ethanol and water, To what temperature would you need to heat it to make sure that all the ethanol vaporized but none of the water vaporized? What is that process called? What process are we talking about here? So the idea behind distillation, you have a container and you have a mixture of two compounds in here, two substances. So it might be water and ethanol, it might be anything. It could be water and gasoline, it could be cooking oil and rubbing alcohol, it could be anything. You have two substances and they have to have a slightly different boiling point. If you heat this mixture until it gets to a point where you can vaporize one of those substances, then you can collect that vapor and have a pure substance over here and a pure substance over there. So you have probably seen distilled water. Distillation of water is a common method for purifying water. You have other impurities in the water that boil at typically a higher temp than water. So you vaporize the water, you collect the steam, you recondense it, and what you have is pure water. This is how ethanol is removed from water, or actually, in that case, they're really more interested in removing the water from the ethanol. So, what you have to look at is the difference in the normal boiling point. What do you have for number 6? Give me an answer, somebody. Claire, give me an answer. 75. Who's got 75? Okay. Who's got 80? Who's got 90? Who's got anything other than those? Okay. Most of you said 75. So here's the caution. And 75 isn't an unreasonable answer, but if you're getting this system up to 75, that is pretty much the exact boiling point of ethanol, and you want to make sure that all of the ethanol goes. Actually, the boiling point of ethanol might be closer to 80. That's probably too low. So what you want to do is you want to make sure that you're above the boiling point of whatever substance you're vaporizing, but well below the boiling point of the other. The closer those two boiling points are, the harder this is. You know, so water and ethanol aren't too bad because it's about 80 and about 100 depending on pressure. If you get this mixture to 90, that's fantastic. At 90, there is no risk that you're going to start to vaporize the water, but you're definitely going to get all the ethanol. You know, you're definitely going to. I mean, I shouldn't say there's no risk. You're going to vaporize some water, but you're not going to vaporize a tremendous amount of water. It's not going to really start phase changing. The ethanol, however, is all going to be boiled off. So, and actually in like commercial distillation, they do multiple distillation steps because you do get some water vapor in with the ethanol each time. So then they redistill, and they keep doing that because you're getting smaller and smaller amounts of water mixed in. Okay, so about 90 will get us all the ethanol removed, and we shouldn't lose any of the water. What about the next one? If we have ethanol and diether, where do we need to take that to make sure you get all the diether vaporized, but none of the ethanol vaporizes? Who's got a number for me? Okay, who have I not heard? Jake, I haven't heard from you.
Well, originally I had 25.
Ooh, too low.
So I'm gonna guess 30.
Ooh.
35.
He's just throwing out numbers here.
Well, I'm going above, but like to get all of it.
You want to get all the diether.
I'm 50.
Okay, you're gonna go with who else has? We'll start with your 25. Anybody else want to use Jake's distillation apparatus at 25? I'm sorry, I'm not in. Okay, who wants to go to 40? Who wants to go to 50? I want to go to 50. Now, the nice thing about the diether and the ethanol, they have a much wider gap in boiling point, so you can pretty safely take that. I mean, ethanol's sitting around probably around 80. You can take that mixture pretty high and not vaporize a lot of the ethanol. So you can certainly take it up to about 50. Okay, At 500 torr and 75 Celsius, which of the substances on the chart above would still be in a liquid phase? Okay. Do you have 4 things written down? What we're looking at is at a given pressure and temperature, which of those things at 75 Celsius still have a vapor pressure that is below 500. So I want you to look at the ethylene glycol line, number 6. Who here knows where they could find ethylene glycol at home? Do you think you know where you could find ethylene glycol at home? Raise, I don't know, twitch, blink, stick your thumb on your forehead, make deer antlers, I don't know. No? Ethylene glycol? No?
For some reason I think it's in glue.
No, no, no. It's very dangerous to pets. Probably wouldn't find it in the house. You'd probably find it in the garage, or the shed, or the barn. Not oil. Yeah, ethylene glycol is antifreeze. So, what is the purpose of antifreeze in an engine? Keeps it from freezing. Okay, does a couple other things. We're going to talk more about ethylene glycol as we go. So this will, I'll glance at those and give you a few points for practice for tomorrow. Now, let's go back to some more notes. I know you're excited. So this kind of sums up what we've just done, talking about boiling, talking about the fact that boiling occurs when the equilibrium vapor pressure is the same as atmospheric. So we talked a little bit about, where we would see increases or decreases in boiling point, how we can sort of manipulate boiling point for various liquids. That's what we just did. Now, we're going to talk about the amount of energy that it takes to vaporize something. So this is molar heat of vaporization. We are not going to do any of the math with this. We're not going to do any of the calculations. If you're going on in chemistry, this will probably be part of your first year of chemistry. This is like a Gen Chem 2 or 3, depending on whether you're on quarters or semesters. What you need to know for now is that this is how much energy it takes to vaporize 1 mole of something. So things that have stronger bonds of attraction have higher or lower boiling points. This is kind of a review. Stronger bonds of attraction internally, boiling points are higher or boiling points are lower? Higher. Yeah. Because those molecules are held more tightly. If something has stronger bonds of attraction and a higher boiling point, does it take more or less energy to vaporize a mole of it? More. It takes more energy. So, every single substance known to humankind has a characteristic heat of vaporization. This is one way you can test to see what a substance is. Try to vaporize it. What's its boiling point? How much energy does it take to vaporize it? And that starts to give you a clue about what you're dealing with here. Water is kind of interesting. We've talked a little bit about this, not much. What 2 kinds of internal intermolecular forces does water have going for it? Remember, we always say water's only attracted to 2 things in the entire universe. Itself and everything else. What 2 forces internally make water so attracted to itself? Hydrogen bonding and what else? Water is what kind of molecule? Polar. It's a polar molecule. So it's got areas of partial charge on either end. So those line up, plus you have hydrogen bonding. Water is really attracted to itself. Narcissistic little molecule that it is. Water has a higher molar heat of vaporization than we would expect otherwise from a molecular compound of its composition because of those strong internal forces. This is why water makes a really good cooling agent. Water makes a good heat transfer agent because it takes a lot of energy to heat that water up. It takes a lot of energy to vaporize it. So, back to the question about ethylene glycol. Ethylene glycol is also known as antifreeze. Why do we use antifreeze? Not just about freezing, kids. Why do we use antifreeze? To protect your engine against freezing and overheating. So look at the line for ethylene glycol. Look at the line for water. Which of those two substances is going to be able to absorb more energy before it vaporizes? Yeah, the ethylene glycol is going to be able to take a lot more energy before it vaporizes. That means it protects your engine to higher temperatures. If in the summer if you have a leaky radiator, you're just putting water in there, because I don't need an antifreeze, and you're just filling with water, your engine is not as protected as it should be against overheating. You can still overheat with a radiator full of water. Now, probably not around here in more extreme conditions than we have, but there are always stories of people in the deserts out west, like crossing the Mojave Desert, where it's 120 out there and your engine's heating up on its own. If you're just using water, you're very likely to cook your engine. So things that have high molar heats of vaporization require a lot of energy before they're going to vaporize. Okay. Now, we get to talk about two of the other transitions that we referenced yesterday, but we didn't talk about so much today. Freezing point. This is where solid and liquid states are in equilibrium at a atmospheric pressure, 1 atm. So just like we had with the liquid vapor equilibrium, when a solid and a liquid phase are in equilibrium, we have opposing changes happening at an equal rate. So we have that one in, one out, one in, one out. And when things are transitioning to a liquid, so when we have a solid that is melting, that's transitioning to a liquid, that solid has to absorb heat to become a liquid. If we have a liquid that's transitioning to a solid, it has to give up heat energy to become a solid. And when we have those things in equilibrium, that's just an exchange of energy. So the solid molecules are absorbing energy from the liquid, which is giving it up. And it's just doing that transfer, 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 transfer. I know that I have drawn this picture for you before, and I'm going to tell you a story because you know I love stories. When I was a kid, when dinosaurs roamed the earth, there were still a lot of places that had pretty large strawberry patches in this county. And the farm next to my grandparents' farm, Burdell Heck's place, had probably 5 acres of strawberries. He had a pretty sizable strawberry field. And how many of you have picked strawberries? Okay, when are they ripe? When are they ripe? When do strawberries ripen? When?
Our strawberries ripen in the fall.
Okay, the big commercial crops typically come ripe early June. Yeah, they're typically June bearers. You can have everbearings, but most of the big commercial places, those are available early June. So all through May, those strawberry plants are sitting there with buds on. They have flowers. And those flowers will become, given bees and good conditions, fruit. So when I was a kid, Burdell would very often on cold May nights, we get a few of those where we get a frost in mid-May. We used to get more of them than we do now. And on a night when we were forecast to get a frost, Burdell would pull out all the irrigation equipment. And he'd be pumping water out of the pond, and he would soak the behoozes out of those strawberry fields. Like the plants would just be dripping, dripping, and he'd run irrigation on them all night. He'd start the pumps at sunset, and he would run pumps all night long. Those fields were like a spongy. And the plants were covered. And I, as a kid, would say, "What's he doing, Dad?" And I would say, "He's saving his strawberries. That's what he's doing." So how is he saving his strawberries? Okay, so let's talk a little bit about what's happening here. If we have a substance that's going from a solid to a liquid, we have this amount of energy difference. Is that energy being given up to the environment, or is it being absorbed by the substance if this thing is going from a solid to a liquid? Being given out to the environment or being absorbed by the substance? It's being absorbed by the substance because the liquid has more energy than the solid did. If something is going from being a liquid to being a gas, this amount of energy, where's it going? Out into the environment or being absorbed by the substance? Absorbed by the substance, okay. Now, what if we take the opposite tack? What if we say that some substance is cooling down, it's condensing from a gas to a liquid? Where is that amount of energy going? Is it being released to the environment or absorbed by the substance? It's being released out to the environment. What if that substance is going from being a liquid to being a solid? What's happening? Is it being released to the environment or absorbed by the substance? It's being released to the environment. If the environment is a strawberry plant that's right underneath you, guess what that water is pumping into the strawberry plant all night as that water freezes? Heat, energy. So you save the strawberries. In the morning, the strawberries are covered in sheets of ice. The leaves are covered in ice. But the water inside the leaves did not freeze. That's what kills plants. That's what kills fingers too, frostbite. The water inside the cells, whether it's in your fingertips or whether it's in the leaves of a strawberry plant or the flowers of a strawberry plant, freezes. That water expands and breaks the cell. And then the cell's done. The cell's dead. Can't recover. In a strawberry plant, that would kill the blossoms. That would kill the fruit. You wouldn't get a crop. But if you have liquid water hitting that plant all night and freezing, the liquid water is going to freeze on the surface. But the plants themselves, the cells within the plant, are not going to freeze. And so you've just saved the whole crop because of this very simple principle. Now, that amount of energy that it takes when we're going from solid to liquid or liquid to solid, that's not molar heat of vaporization. That's molar heat of fusion. So it's the same relationship. It's that amount of energy that exists here between the solid and liquid state. The thing that I always find confusing and counterintuitive is that it's the amount of energy that we need to melt a mole of a solid. When you say fusion, I think going from liquid to solid, but it's not. It's actually the amount of energy required to go from a solid to a liquid for 1 mole. I just think they named it badly, but I wasn't consulted. They didn't ask me. Same for molar heat of vaporization. When you have a bigger molar heat of fusion, it's indicative of stronger forces of attraction. If there are stronger forces of attraction intermolecularly, it's going to take more energy to move those things apart. Okay? That is actually where we're going to leave our chemistry heroes, because we're going to start phase diagrams tomorrow. So tomorrow we'll be doing some practice with phase diagrams. Thursday, actually you're going to do 2 things tomorrow. When you come in, you're going to have a FIP quiz over the vapor pressure stuff. And then we're going to work with phase diagrams and do some practice with that. Thursday we will have a phase diagram quiz. And I would love to have your test be Friday, but there's some sort of event going on. I don't know what it is, but I guess a bunch of you aren't going to be here in the afternoon. I don't know. So we'll be doing the big quiz on Monday. So there'll be a quiz over really this stuff. It'll be conceptual, probably 10-question conceptual, and then a workout that's very much like this and the phase diagram stuff you're going to see. Questions, comments, concerns? Okay, wunderbar.